Let's look at our first example. We want to use the simplex method to find the minimum value of w, which is a linear function, 3x1 plus 2x2, and subject to those two constraints. 2x1 plus x2 is greater than or equal to 6, and x1 plus x2 must be greater than or equal to 4, and under those positive values of x1 and x2. So in the case that we have only two variables involved, you can also solve this problem, the problem of minimizing the value of w by using the graphical technique that we learned before in section 9.1, okay? Because when we don't have that many variables involved, the graphical technique is quite useful and we don't have to spend time in writing the simplex matrix or simplex tableau at all. Okay, but we would like to practice now in using the simplex method for minimization problem. So first, we write the augmented matrix corresponds to our minimization problem. Again, in this portion, we put all the coefficients of our variables. The first column, we put down the coefficients of s1, which are 2 and 1. So that falls into the first column there. Okay, the second column is just for the coefficients of your variables x2. And on the right portion of your augmented matrix, you put down all those numbers on the right hand side of each constraint. Okay, in the bottom row, you put the coefficients of s1 and s2 in this portion, and on that spot, you put 0 for w. After you've got the augmented matrix corresponds to your minimization problem, you then take the transpose of that augmented matrix. Here's the transpose, okay? So you take the transpose. After taking the transpose of that augmented matrix, you got this one, and that matrix, the resultant matrix, will correspond to the dual maximization problem. So we can then write the dual maximization problem. So I'm going to rename all my variables previously. If you look back to your original problem, the variables are s1 and s2 when you want to minimize w. Now I'm going to rename my variable. I'm going to set the new variable as the variable y1 and y2, okay? So over here, in this portion, you're going to get the coefficients of y1 in the first column, and coefficients of y2 will be put in the second column. Alright, so corresponds to that portion of the coefficient values of the variables y1 and y2, I've got those two constraints. 2y1 plus y2 less than or equals 3. The inequality sign will be changed from greater than or equal to lesser than or equal. From the second row of your matrix, after you have taken the transpose, you're going to get y1 plus y2 less than or equal to 2, which is that number. Okay? But you also still have the non-negative constraints of your variables y1 and y2. Last row or the bottom row will give you the coefficients of the dual maximization problem. So here, you have your new objective function is to maximize your z as 6 times y1 plus 4 times y2. So the dual maximization problem is to minimize z as a function, a linear function, that can be written as 6y1 plus 4y2 under those two constraints. Okay, now the simplex method that we learned before in section 9.2 can be used to solve this maximization problem. By seeing that we have two constraints of our dual maximization problem, then it means that by using the simplex method, two constraints over here, then we have to add two slack variables. So I'm going to say we have to add two slack variables. You still remember that? We learned in last class. Okay, so let's add the slack variables and change. By adding the two slack variables S1 and S2, we can change the constraints from inequality constraints to equal constraints as follows. So we want to maximize z equals 6y1 plus 4y2 subject to the constraints. So the first one, by adding the first slack variable as 1, the first constraint is going to turn out to be 2y1 plus y2 plus s1 equals 3. And the second constraint, by adding the slack variable s2, the second constraint will be changed to y1 plus y2, and then plus s2 equals 2. And we still have the non-negative constraints y1 and y2, both must be non-negative. So by seeing this maximization problem, it's just the dual maximization problem that we have added the two slack variables. We can then start writing the initial tableau and then start using the simplex method. Okay, I put the initial tableau in the next page. Okay, you still remember how to put, let me move this down a little bit so that you can compare, just in case that you have forgotten how to form the initial tableau of the simplex method. Okay, since you have two constraints, okay, and one objective function, your initial tableau will have 3 rows in it. Okay, the first column is for the variable y1, second column is for the variable y2, third column is for the slack variable s1, and then the slack variable s2, and then that is for z, and that is for the right hand side. I name it to be b. Okay, so out of the first row, you put the coefficient of y1 there, coefficient of y2 there, and then coefficient of s1, which is 1. You have no s2 in the first row, so you put 0 over there. There's no z variable in your first row, then you put 0 over there, and your constant term appeared on the right hand side is 3, so you put 3 there. Same idea for the second row of your initial tableau. You put the coefficients of y1, which is 1, coefficient of y2, which is 1. There's no s1 in your second constraint, so 0 s1 goes there. And you have 1 s2, so you put 1 here. There's no z variable in your second constraint, so you put 0 over there. And also the constant term on the right hand side of your second constraint is positive 2, so you put constant 2 right over there. In last row or in the bottom row, okay, you get it by rewriting your objective function. So let's look at the objective function one more time. I'm going to move everything to the left hand side. Okay, move everything to the left hand side. It means I subtract of both sides by 6y1 and also subtract of both sides by 4y2. So that's going to be negative 6y1 minus 4y2, and then plus z equals 0. And then after I have rewritten that with the pink color, I put the coefficients of y1, which is negative 6, right at the bottom row, negative 4 as the coefficient of my y2, right there in that spot. There's no s1 variable, no slack variable s1, so you put 0. No slack variable s2 in your objective function, so you put 0 there. You get 1z, so you put 1 right over there. The right hand side is 0, so you put 0 in that spot. So over here, the non-basic variable, you still remember the non-basic variable? The non-basic variable over here, there are 2 of them, S1 and S2. So I put that in that column. okay? And next, we're going to determine the entering variable and the departing variable by looking at the last row or the bottom row of your initial tableau. The most negative entry is -6. By seeing that the most negative entry is -6, so the entering variable is y1. So this is entering. Okay? And after you have known that y1 is the entering variable, so I'll put a little note saying that y1 is the entering variable. We have to determine what is going to be our departing variable. So by computing the ratios, so we need to compute the ratios. So to compute the ratios, out of the first row, you divide 3 by 2. So divide 3 by 2. 3 divided by 2. That makes 1.5. And the other ratio is 2 divided by 1, which is a 2. So out of the two values, you take the smallest non-negative number between 1.5 and 2. Both of them are positive, but the smallest non-negative number is 1.5. So we're going to go with that ratio. That means your S1, the ratio of 3 over 2 or 1.5, you got it from the first row. And it implies that your S1 is going to be the departing variable. So I'm going to put a note saying that my S1 will be departing. Okay, so S1 is the departing variable. So we know that S1 is the departing variable. We're going to use Gaussian elimination. Okay, try to get the leading one in that spot. That means I'm going to divide the first row by 2 just to create a leading one in that spot. Or you can even say that this is going to be to a pivot number. Or pivot element. Okay. So I'll just go ahead, divide the first row by 2. And after I've got one in that spot, I can use that leading one to get rid of those two numbers underneath. So I do the calculation already and put in the slides, okay? I bring the initial tableau and put it over here. And that is my pivot number, okay? To make life easy, I divide the first row by 2. Just to create a leading one. So I'm going to highlight that as well. That is my pivot number, okay? Divide by 2. Then I get the leading one. And then I can perform 2 elementary row operations to get rid of those 2 digits underneath. Okay, to get rid of that constant 1, I perform R2 minus R1. With that elementary row operation, it's going to make changes to this spot to become 0. Same idea, I want to get rid of that -6, which lies underneath of that my pivot number. So to perform the row operation to get rid of that -6, I perform R3 plus 6 R1. And then I can eliminate those 2 spots to get 0 in those 2 spots. After we've got that matrix, I'm going to call that as my second step of the Simplex tableau. So I'm going to put that matrix once again in the next slide. I put it already over here. Okay, let's take care of the non-basic variables. A moment ago, S1 departed already, and the entering variable was y1. So this spot will be changed to y1. So the non-basic variable is going to be y1 in the first row, and that just remains S2 as the previous step, okay? And we start using the Simplex method once again. We look through the bottom row, and search for the most negative entry. We see that the most negative entry is -1. So I'm going to highlight that. That is the most negative entry. So the entering variable out of this step is going to be y2. If you want to label all the variables up top, that's fine. Variable y1, variable y2, the slack variable is 1, the slack variable is 2, z and b, the constants appeared on the right hand side of each constraint, and also the right hand side of your objective function is currently 9. Okay, the most negative entry is -1, so the entering variable is going to be your y2. So I'm going to say entering, or you can put a note saying that y2 is the entering variable. The entering variable. By knowing that y2 is going to be our entering variable out of this step, we have to also determine what variable is going to be the departing variable. So to determine the departing variable, we again compute the ratios. Okay, we're going to move on to compute the ratios. Out of the first row, now we focus at b and y2. Finding the ratio between b and y2. Okay, so the first ratio is 3/2 divided by 1/2, and that gives me 3. The next ratio is divide 1/2 by 1/2, and that's going to give me 1. So 1/2 divided by 1/2. Just divide this guy by that guy from the column of y2, which is the column of the entering variable. So the ratio turns out to be 1. Then we compare between those two numbers. This is the smallest non-negative ratio, so I'm going to highlight that. The smallest non-negative ratio. And I got that ratio by dividing b2 of the second row by dividing b of the second row by y2 in the second row. So it implies that S2 is going to be the departing variable. So S2 will be departing. So put over here that S2 is the departing variable. The departing variable. So you're gonna try to get a leading one out of that spot, and after you've got the leading one in that spot, you will use it to get rid of everything else in that column. So this guy must be gone, and that guy must be gone as well. So I'm gonna bring this Simplex tableau and put in the next slide, okay? And then I try to use Gaussian elimination as usual to get leading one in that spot, and then get rid of those two spots afterward. Okay, I put this matrix, okay, over here. This is the pivot number. That is my pivot number because S2 is now the departing variable. So to make life easy again, I multiply the second row by 2 just to get a leading one in that spot. So this is again my pivot number. After I've got the pivot number, I use that pivot number to get rid of everything else in that column, column y2, or the column that contains the coefficients of variable y2. So to get rid of this guy, I perform R1 minus 1/2 R2. And to get rid of this guy, I just add those two rows together by adding R3 with R2 and put the changes in R3. I get that matrix. If you want to put a straight line to separate your constraints and the objective function, that's fine. Or you can keep it without writing down the straight line, okay? So, after I have performed elementary row operations, 3 row operations altogether, I obtain this current simplex tableau. So the non-basic variable out of this step, Okay, back into the previous step. The first row, the non-basic variable is y1. We just copied from the previous step. Previously, in the previous step that we just went over, y2 is entering and s2 is departing. So the non-basic variable for the second row is now your y2. Okay? You get the non-basic variable as y1 and y2. Now let's look at the last row or the bottom row. You no longer have negative entry in that bottom row. It means that you have reached the maximum value of z, and the maximum value is 10. The maximum value is 10. So that is the maximum of z. And that occurs when your y1 is 1 and your y2 is 2. Okay? Maximum is 10. It occurs when y1 is 1 and y2 is 1. To read for the solution to our original problem, which is to minimize w, this is also the value of the minimum value of w, and it occurs when x1 is 2 and x2 is 2. So I'm going to highlight those and put the summary saying that the minimum value of w is 10, and it occurs when x1 is 2 and x2 is 2. So x1 equals 2 is this guy, x2 equals 2 is that guy. So you can read the solution or the minimum value of w from the latest Simplex tableau.